right, perhaps we better get started. Are you ready to go, Zeishan?
Yes.
All right. So, good morning, everybody. Thank you for joining us for this morning's Astrophysical Science and Technology Master's Defense. Today's candidate is Zeishan Mohammed. And in a moment, I'll ask his advisor, Richard O'Shaughnessy, to say a few words of introduction. But first, the formalities. Zeishan will speak for around about 45 minutes. And after that, there will be a question and answer session. So to allow Zeishan to keep time, please either type your questions in the chat or leave them until the end of the talk. Following the talk, there will be a closed meeting of the committee. So at that point, we will ask everybody who is not part of the committee to leave the call. All right, with that, I'll hand over to Richard to introduce today's candidate. Richard.
Hello. Assuming people can hear me, and someone should indicate if they can't. So Z's been working with me for a little bit on understanding the population of gravitational wave sources. This is a really interesting time in gravitational wave astronomy as we transition from having one to few to many to potentially very soon very many. And we're starting to unveil and have access to new and interesting features. And that is what Z's thesis is about probing the frontiers, and a particularly interesting frontier that I think he'll soon elucidate, talking about first steps using population inference of first with non-spinning eccentric binary clouds. Z, take it away.
Okay. Can you hear me?
Yes.
Yes. Okay.
Yes, fine.
Okay. Hello, everyone. I'm Mohammed Zeishan, and I'm working with Professor Richard.
Recording in progress.
On a population inference of non-spinning eccentric binary black holes. So let's start with the contents first. So I will give brief introduction of black holes, then binary black holes and their formation, then gravitational waves, and then why eccentricity is important, and then why we study population, and then our results, our analysis about the inference, and at the end I will give a summary and I will talk about my future goals. So let's start with the black hole. So we have two images over here. So first of all, what is black hole? So black hole is a mysterious and extremely dense region in space-time, and it has a very strong gravity. Even light cannot escape it, and we can call them a simplest object as well, because we can characterize them with mass and spin only. And there are three main things in that right hand image, that is the artistic view of the black hole, and you can understand three things about it. Like first of all is the singularity, like the extremely dense core of the black hole. And second one is the event horizon. The event horizon is that boundary over here, and we can call it the point of no return. Like if you pass this particular region, there is no way back. That is called the event horizon. And the third thing is the accretion disks that help us to detect the to see the black hole. Basically, there's a gas and matter that is revolving around the black hole with a very high speed, close to the speed of light, that emit the electromagnetic radiation in different spectrum. So we can detect the black hole we can see the black hole with the help of accretion disk. If there is no accretion disk, we may not be able to see the black hole. And the left hand side, that is the very first image of our own galaxy black hole, Sagittarius A black hole. And the brighter part of this region over here, they basically show about the overall the orange thing is basically showing the accretion disk, and the center darker region is basically image of the black hole, because we can it is the shadow of the black hole. We cannot see the black hole, but that is the shadow of the black hole. And the brighter regions, they show that the matter that is revolving in the accretion disk that is coming toward us, and the fainter regions shows that the matter is going away from us. So that is the kind of a brief introduction about the black holes, and then we will move forward about the types of the black hole. So based on the size and the origin, we have we have three types of black hole: primordial black holes, stellar black holes, and supermassive black holes. Primordial are the smallest ones, and they're thought to be made due to the direct gravitational collapse of subatomic matter right after the Big Bang. And the stellar black holes, that's what we am going to discuss in this talk. They are made of they get born out of the death of a star, and particularly the black holes, the mass of a zero age main sequence star should be greater than equal to 20 solar masses. Then we can get a black hole. If you look at the lower panel of the image over here, so we have a main sequence star. Main sequence star is just like it's burning hydrogen in its core, and then when it gets run out of fuel, like basically the hydrogen, then it becomes a red supergiant. And ultimately, due to the gravitational imbalance, like internal external force, we have a supernova. And then we will get after the supernova, that core will become a neutron star, or we may get a black hole. So that's how we get a stellar black holes, and that's what we are going to discuss in this talk throughout. And the third one is supermassive black holes. They have a million of solar masses. They are extremely they have extreme masses, and we thought they are born with their parent galaxy, and they are usually in the middle of the galaxy, the supermassive black holes. But the focus of this talk is particularly on the stellar black holes. And after the black holes, now we will discuss about the binary black holes. So for the binaries, we have two different formation scenarios. First of all, isolated binary evolution, and then dynamical evolution, like dynamical captures. So on the left hand of this panel, that shows that the isolated binary evolution. Let's suppose we have a two main sequence star in an isolated environment, or you can say that in the less dense environment, and they are already stars are in the binary, and they are orbiting around each other, and one of them gets into the red supergiant phase and collapse into a black hole, and they are still in the binary. And we have a common envelope phase, like the mass is going from from the star to the black hole. And there are two scenarios after that. Is if the common envelope ejected, yes or no. If the common envelope ejected, then we are left with the star, and the basically helium core star, and then it will collapse into the black hole, and ultimately these two black holes revolve around each other, and then we will get a merger. And the right hand panel, that shows the dynamical formation scenario. Like we have a binary of a star, one of them goes into the supergiant phase, we have a black hole, but because they are in the dense environment, so they may have a gravitational encounter, third body encounter, and that basically disturb their orbit, and they may form binary, but due to the dynamical encounters, the binary, the circular orbit may get disrupted, and we may get a eccentric orbit over here, and ultimately we will have a merger. So why I'm focusing on that, then on the formation scenario, basically when you have isolated one, the circular orbit may be circular, but when you have a dynamical encounter, the dynamical formations, then the orbit, they can be eccentric. Okay, so now the gravitational waves. So when the two black holes coalesce around each other, they produce the gravitational waves in the space-time. And when they produce the gravitational waves, so those gravitational waves carries the information of the source. It can be mass, it can be spin, it can be eccentricity. So the gravitational waves have those information in them. And we detect them by the LIGO, VIRGO, and KAGRA network. The very first detection was made by the LIGO, and that is a very basic schematic of how we detect the gravitational waves. So basically, we have a laser light from here, and it goes to the splitter, and then it split that laser light into two different ways, into different arms. And what we do, we basically measure the change in the length of the arms. If the gravitational wave hit passes by those detectors, they basically change the length of the arm. In a scenario like one of them get extended and one of them get contracted, and if that happens, then we will see some signal of the light over here. In normal scenario, when there is no gravitational wave, the light that goes to the mirror and come back from in the both arms, when they reach at the detector, they basically cancel the effect of each other, and then we do not see any light. But when there is a gravitational waves, we do see some signals due to the change in the length of the arm. So that's how we detect the gravitational waves. Okay, so this is the lower panel that shows the waveform. Basically, there are three different phases of a merger. The first one is in spiral one, like when the two black holes get gravitational bound, so they basically produce basically symmetrical gravitational waves. And when they get closer, when the merger is going to happen, their orbiting speed get increase and increase, and we will have a higher frequency over here, and ultimately they get merged and settled on phase, and we have no signal over here. So these waveforms basically plays a role, very very important role, that they have the information about the mass and spin in it. We will discuss it later. So there are two different waveforms we have over here: circular and eccentric waveforms. In the left hand panel, we have a circular orbit, like we have center mass. Object is the black holes. They are orbiting around each other, and you can notice that they have a constant speed and a constant distance on the left hand panel. But on the right hand side, we have an eccentric orbit, and you can see that the speed of the black holes varies, even the distance between them. Like when they reach closer to the center of mass, their speed increase and their speed decrease over here. So that kind of a effect we can see in the waveforms. Like if you look at the black waveform, it's pretty symmetrical waveform. The amplitude is constant, the distance between them constant. But if you look at the red colored waveform, that is the eccentric waveform basically, and it have the different complicated shape, because it depends on the speed and the distance between the black holes. Okay, so keep talking about the waveforms, like because the waveform plays the role to detect the gravitational waves and to infer their properties. So but we have that is the on the top panel, we have the actual signal that was detected by the LIGO, and we compare it with the numerically produced template of the waveforms, and after comparing it, we were able to infer the properties like mass and spin and other like distance and location with the waveform, because each waveform has a unique pattern that display the properties of the merger. And we call this method match filtering technique. Like we have a bank of templates and we compare it with the observed signal, and then we infer the properties of the merger, and then we tell what kind of mass and spin they have. Okay, so from 2015 to till now, that is the published events we have. There are more than 90, and we call this the stellar graveyard. And the blue ones, we will focus on the blue dots. They basically present the black holes. And if you look at the vertical things, like over here, like this is the first 2 points, they are the original masses of the black holes in the binary, like primary and secondary masses. And the third dot over here, that is the outcome of the merger, like the remnant of those mergers. So if you look at them, like the most of the black holes, they are in the region of between 10 to 50 solar masses. The remnants, they are more than 50, they have the mass more than 50, but most of them, the original masses of the binaries, they lie between the 10 to 50 solar masses. So that is one of the reason, like we choose those masses in our research to make our inference about the whole population. Okay, so why eccentricity is important for us? Like because the orbital eccentricity that have the unique signature of the formation of the binary, and it can tell us about the environment and the formation about the binary, because the if the binary is in the isolated environment, it would have a circular orbit. But if the binary is in the dense cluster environment, then it may have the elliptical orbit. So to better understand the formation and evolution scenario, eccentricity will play the key role to understand it. Okay, so why eccentricity, and now why population? Like why we focus on the population instead of a individual event? So you can just take it as a sample mean. Like if you have a one individual detection with some uncertainty, like with some measurement error, so you will have some idea about that binary. But when you get a more than one, then including their error, we can take the average or a sample mean. The error will get reduced. Same with if we take a whole population, like if we have a more bigger sample, the error will get reduced. So that is the one of the reason to study the population. Okay, that was the basic background, like why I'm doing, and now the basically schematic, like how we made the inference, like what ingredients we need to make a inference. So first of all, we need population, and sensitivity model. They can be mathematical model. First of all, we need a model basically, and then we need the data. It can be real or it can be synthetic data to constrain that particular model. So in our research, I have used the modified power law model, and I have used a synthetic population, not the real population, because the real population we do not have enough eccentric waveform. So in the real detection, we do not have a eccentricity component in it. So that's why to take our model, we will use the synthetic population, and to constrain the model parameters, we will use the Bayesian inference. Okay, so first of all, model. So the modified power law model. So in this model, we have the m1, m2, and epsilon. These are the basically masses of the binary m1, m2. Epsilon is the eccentricity of a single event. Like m1, m2, and epsilon, they are the parameter of the individual source, like for the one binary. And on the right hand side, those parameters, they represent the whole population, like the minimum mass in the population, maximum mass, the total mass, and the sigma e, basically that show the eccentricity distribution, and alpha is the power law index. So we use this power law model. We modified this to add the Gaussian eccentricity in it, and we will use this for the population inference, and we will create a synthetic population by using it. So we have a model. Now we need a population, like the data. Like data mean like each event in the data would have the mass and eccentricity component. So we have created that synthetic population because we do not have a real events. So we have a eccentric population, non-spinning, non-precessing, and the masses would be between 10 to 50 solar masses. And we have imposed the condition m1 is greater than m2, and that we also impose the condition like the total mass would be equal to 100 solar masses. The total mass will not exceed the 100. And we have generated 10,000 events for the synthetic population first, that you can see in the 3D figure over here. That color spectrum shows the eccentricity of each event, and you can see that is the complete population that we have produced with this modified power law model. And then what we did next, like we used the LIGO sensitivity by solving this integral over here, where d of z is the luminosity distance, dh is basically the horizon distance which the source can be seen, and vc is the co-moving volume, and z is the redshift of the merger event. So we solve this integral, and that plot shows the sensitivity we considered for our analysis, and we applied it on our synthetic population for the weighting. So if you look at that figure, the sensitivity is it's more sensitive at the higher masses, like 100, between 100 higher masses and equal masses, and it's very less sensitive at the lower masses over here. So that sensitivity effect can be seen in our final synthetic population, because we have out of 10,000 synthetic events, we have weighted down them to the 100 by by considering the LIGO sensitivity. So out of these 10,000 events, we have weighted down these 100 events to make our inference. And you can see in that image, like, because the sensitivity is, we have a lesser sensitivity at the lower masses, so that we have very low masses after the weighting in the lower mass region in that figure, and the higher density at the equivalent higher masses. Okay, after weighting, we have 10,000 events, synthetic events, and then we have weighted down to the 100 events, and then to make them real, look like real, we have added the measurement error in our synthetic population by following the Illiam-Mandel paper, that schematic. So the synthetic population we have, they have the M1, M2 and eccentricity in it. So we didn't add the error directly to the primary and secondary masses. We basically converted them into the M chirp and the symmetric mass ratio eta and MC, because they are well constrained with the real data. So that's why we converted our synthetic population masses to the chirp mass and symmetric mass ratio eta, and then we have added error into them, and by using this equation that is defined in that paper. And the beta is the scaling component over here, and R naught is the random number, and it basically shifts the mean of our population over basically masses. And rho is the signal to noise ratio, and we have followed the LAL inference scheme, and we take the rho greater than equal to 8. And after adding the error in M chirp and eta, we converted it back to the M1 and M2 to make our inference, because to make our inference, the data should be in M1, M2 and eccentricity. So we have taken the synthetic data we have produced, we have converted it into the M chirp and eta, and then we have added error in M chirp and eta, and then we have converted it back to the primary and secondary masses to make our inference. So after adding the error, our posterior would look like this, like the banana shape, like they have the single event, but we have added the element error, so this shape should look like that. I have taken this image from this paper, like from the same schematic they have introduced the equation, so that's the figure from there. So in that's the synthetic population we have. After adding the error, we get that kind of population. Okay. So the next thing what we did with our population to make the comparison between the model with eccentricity and model with model without eccentricity, we have used this equation and defined in that Fawata et al. Paper, and we have omitted the eccentricity component from our population, and in this image you can see that the blue dot, they have the eccentricity component in them, they are eccentric binary black holes, and the orange ones are the non-eccentric binary black holes. So the blue ones, like you can say the mass is almost identical, there isn't any significant mass shift after omitting the eccentricity, except few events, like that one event you can see that there's a minor shift in the orange dot, and that may be because of the event would have the eccentricity is equal to 0.05, because the greater the eccentricity, the greater the effect of the mass shift. So the mass shift from the left hand side. So because we have taken the modest eccentricity 0.05, so that's why we are seeing the very minor effect on the mass shift. But yes, if you have the higher eccentricity in your population, then the mass shift would be greater. Okay, so till that stage, we have our synthetic population, including the LIGO sensitivity and measurement errors, and we have eccentric binary black holes and non-eccentric binary black holes. So now the population inference, like how we made the population inference, because we have the model, modified Pavlov model, we have the synthetic population with LIGO sensitivity and with measurement errors. So we need to get the posteriors, so we use the Bayesian inference, and the Bayesian inference, and we have the priors would be uniform in this, because in the Bayesian inference we need the priors, likelihood, and then we find the posterior. So priors are the uniform for the rate, alpha is power law index, and minimum mass, maximum mass, and the eccentricity distribution. These are the injections 2, -1, 10. That's what we have. These are the two values, like we use them to produce the synthetic population. These are the priors we have used. All of them are uniform, and that is our likelihood. That is the Poisson distribution. The mu is the expected number of detections under a given population parameterization lambda and overall rate r, and that small, and that is the likelihood of a data, like for the individual event, not for the whole population. That's the likelihood for the individual events, the rate and the probability of lambda at given lambda. Small lambda over here, keep in mind, like the small lambda, this represents the parameters of the individual events, like in d1, d2, d3. Like d1 mean the event 1, merger 2, merger 3. So small lambda have all the parameters of each individual events, and the capital lambda, this shows the parameter of the whole population basically. So we use this likelihood, and because that is a complex integration, we cannot solve it analytically. So I have used the Monte Carlo Markov chain method, that is a sampler. So we use this to get our posteriors and to infer those parameters. So the very first result we get from our MCMC method, we basically, in this figure, what I'm trying to explain and show you is that I have taken different number of injections. Number of injections mean different number of events I have taken, like 5, 10, and I was trying to check like how many number of events at least I need to recover the eccentricity distribution. So the 5 injection, I have some broader bell curve with few, but as we increase the number of events, the bell curve is getting narrows, and we are getting the better recovery with more number of events. And my code is basically producing the equally likely numbers, bunch of numbers, and that's why I'm showing it with the histogram. Okay, that is the corner plot, like for the population inference, and I am trying to compare the inference with the non-eccentric binary black holes and eccentric binary black holes. The orange contour, that shows the eccentric binary black hole inference, and the black contour shows the non-eccentric binary black hole, like we have omitted the eccentricity in the black contours. So if you look at over here in the left image, so the blue ones are the true values, basically the one we have used to create a synthetic population, the injection. And over here you can see that with the full model, like with the eccentricity, we were able to recover the true values, but the without eccentricity, the black contour is basically missing the true value over here. So same, we can see that like we have got better constraint with the with the eccentric binary black holes. And the summary is like we have modified the power law model to add the Gaussian eccentricity, and we have created a synthetic population with measurement error and LIGO sensitivity, and we were able to recover the even modest case of eccentricity in the low mass of binary black hole, even with the 5 events. And the implication would be the eccentricity is useful to understand the formation and evolution better, so that's why we put focus on the eccentricity over here. And the future goal, like in the future goal, like we will have a more sophisticated eccentric templates, and so we will use them. And if we have our real events in future with eccentricity, then we will apply our technique to the real observation. And we are also planning to include a more physics, like in this research, we focused on the non-spinning and non-precessing binary black holes, but we plan to include the more physics like spin in our models to make the inference about the eccentric binary black holes. And because the number of events are going to increase, so the computation cost will be increased with that. So we will focus on to reduce the computation cost by using the deep learning and machine learning methods. Thank you.